So hello, my name is Shubham Oli, and today I'm here to present you my machine learning regression project, which is on bike sharing demand prediction. So this is my individual project. So here, this is my project summary, and this is my GitHub link. This is our problem statement. So here, currently rental bikes are introduced in many urban cities for the enhancement of mobility comfort. It is important to make the rental bike available and accessible to the public at the right time as it lessens the waiting time. Eventually, providing the city with a stable supply of rental bike becomes a major concern. The crucial part is the prediction of bike count required at each hour for the stable supply of rental bikes. So my goal is to develop a model that is highly accurate with a low mean absolute error and a high R squared value. The model should be able to provide insights into the factors that most impact bike demand, helping the bike sharing company to make data-driven decisions about how to optimize their operations. So let's start. So at first, I've imported the libraries. So we have used Pandas, NumPy, Matplotlib, and Seaborn. And for date and time, we use the datetime library. And for machine learning modules, we have used the sklearn. So we use here min-max scaler, one-hot encoder, multi-level binarizer. And for machine learning tools, we have used linear regression, lasso, ridge, and so on. So after that, we mount the drive and import our data set. And this is the first view of our data set. By dot head, we are able to see the top 5 rows of our data set. And by dot tail method, we are able to see our bottom 5 rows of our data set. And here we have 8,760 rows with 14 columns. And these columns are date, rented, bike count, hour, temperature, degree Celsius, etc. This is our dataset information. So we have 6 float, 4 integer, and 4 object data types. This is our duplicate values. So we have 0 number of duplicate values here. And now checking for unique values for each variable. So we have this kind of unique variables. Now checking for missing and null values. So we have 0 number of missing and null values. By visualizing that in a heat map, we can see that we have no null value here. So what did we know about our data set? So we have 8,760 observation and 14 features. So it means we have 8,760 rows with 14 columns. So in a day, we have 24 hours. So we have 365 days a year. So 365 multiplied by 24, it's 8,760, which represents the number of line in the data set. So there are no null values. The data set has all unique values. There is no duplicate, which means data is free from bias as duplicates, which can cause problems in downstream analysis, such as biasing result or making it difficult to accurately summarizing the data. And date has some object data types. So it should be datetime data type. Now understanding our variables. So by dot describe method, we are able to see the count, mean, standard deviation, minimum, maximum, 25th, 50th, and 75 percentile of our columns, our data set. So this is our feature description. So here we have date, which is from 1 December 2017 to 30 November 2018, which is in day, month, and year format. We have rented bike count, so which is the number of rented bikes per hour, which are dependent variable. We have hour, temperature, humidity, and so on. Now pre-processing the data set. So we have 0 number of missing or null values. We can visualize them. So as you can see here, we have a 0 missing values. Now checking for duplicate values, we have 0 number of duplicate values. But some of the columns name in the dataset are too large and clumsy. So we are going to change them. It will not affect our end result. So we are going to change our column name like rented bike count to rented underscore bike underscore count, and temperature degree Celsius to temperature, humidity percentage to humidity, and so on. So Python read date column as a object type. Basically, it reads as a string. As the date column is very important to analyze the user behavior, so we need to convert it into date time format. Then we split it into 3 columns, that is year, month, and day as a category data type. So we are going to break the date column into 3: year, month, and day. So we convert the date column into 3 different columns, that is year, month, and day. The year column in our data set is basically contains the 2 unique number, the details from 2017 December to 2018 November. So if I consider this is a 1 year, then we don't need the year column, so we drop it. The other column, day, it contains the details about the each day of the month. For our relevance, we don't need each day of each month data, but we need the data about if a day is a weekday or a weekend. So we convert it into the format and drop the day column. So here, as we can see, we have weekdays and weekend, and we have dropped the year column. So for weekdays and weekends, zero stands for the weekdays, which are 6,264, and 1 stands for weekend, which are 2,496. So here we will change the data type. So as R, month, weekdays, weekend, column R shows as integer data type, but actually it is a categorical data type. So we need to change this data type. If we not do this, then while doing the further analysis and correlated with this, then the values are not actually true. So we can mislead by this. So we are going to change this integer column into categorical column. So as you can see, we have R, month, weekdays, weekend. So here we have 3 category: 6 float, 3 integers, and 3 object data types. So this is our columns. Now it's time for exploratory data analysis of our data set. So here we are going to analyze the month variable. So here we have plotted one bar graph. So here we can clearly see from the month 5 to 10, which are from May to October, the demand of rented bike is very high as compared to the other months. And these months come inside the summer season. Now for weekdays and weekend, here this is for weekdays and this is for weekend. So here we can clearly see the weekdays have more rented bike counts, and by creating a subplot, the blue one is for weekdays and orange one is for weekends. So here we can see in weekdays, the peak time is from 7 a.m. to 9 a.m. and 5 p.m. to 7 p.m., which is maybe the time of going to office or coming back to home from office. And the orange color represents the weekend days. So it shows the demand of rented bikes are very low, especially in the morning hour. But from evening 4 to 8 p.m., the demand slightly increases. So for same, we are going to analyze for R variable. So from the above plot, it shows the 24-hour of one day. So here we can see generally people use rented bikes during their working hours from 7 to 9 a.m. and evening 5 to 7 p.m. And in these 2 times, only there is a high increase in the rented bike count. So demand is high at the time of going or coming back from office. So over here, this is the functioning and non-functioning day. So here we can see the orange color shows the non-functioning day and the blue color shows the functioning day. As it is non-functioning day, so the demand of rented bike is 0 because of non-functioning day or maybe no working day or maybe any holiday, whatever it may be, but there is no rent. But for functioning day, the count is same as we saw above from 7 to 9 a.m. and 5 to 7 p.m. The bike count is quite increasing. And for seasons, as we can see, we have 4 seasons here: winter, spring, summer, and autumn. And here we can clearly see the summer has the most number of rented bike counts and winter has the lowest number of bike counts. And here the orange color is for spring, green is for summer, blue is for winter, and red is for autumn. So here we can see winter has the least number of bike counts. But in summer season, the use of rented bike is high and the peak time is 7 a.m. to 9 a.m. and 5 p.m. to 7 p.m. So for holiday, bikes are more rented on no holiday, but still they are taking the bike rent on holiday, but there is some specific time. like from 2 p.m. to 8 p.m. But in no holiday, the bike rental is getting high as usual. So as we have already told that in morning from 7 to 9 a.m. and evening 5 to 7 p.m. So is the peak times here. Now analyzing the numerical variables. So here we have separated numerical variables from the data frame, and we have printed the disk plots to analyze the distribution of all numerical variables. So we have our rented bike, temperature, humidity, wind speed, visibility, dew point temperature, solar radiation, rainfall, snowfall. So here, as we can see, the rented bike count, wind speed, solar radiation, rainfall, snowfall, they are right skewed, and visibility and dew point temperature are left skewed. And also our rented bike count is our dependent variable too. So let's try to find out the relation of numerical features with our dependent variable. So here, numerical versus rented bike count. So this is for temperature. So as we can see, people love to ride bike when it is pretty around 25 degrees Celsius, as you can see here. And this is for dew point temperature. It's the almost same as temperature. There is some similarity present. We can check it in our next step. And this is for solar radiation. So the amount of rented bike is huge. When there is solar radiation, the count of rent is around 1000. As you can see here, this is the maximum count. And for snowfall, the amount of rented bike is low when we have more than 4 centimeter of snow. But as we can, if we can see that less than 4 centimeter of snow, the rented bike count goes high, little increased more than this. So now for rainfall, so even if it rains a lot, the demand of rented bike is not decreasing. Here, for example, even if we have 20 millimeter of rain, there is a big peak of rented bikes. So this is for wind speed. The demand of rented bike is uniformly distributed despite of wind speed. But when the speed of wind is 7 meter per second, the demand of bike also increased. That clearly means people love to ride bike when it's little windy. So now this is our regression plot. So this is our rented bike count. It is a linear plot. And here we can see the temperature. It is positively correlated, which means if the temperature increase, the bike count will also get increased. And this is humidity, and it's a negative correlated graph, which means if the humidity will increase, the rented bike count will decrease. So wind speed, visibility, dew point temperature, and solar radiation, they are positively correlated. And rainfall and snowfall, they are negatively correlated, which means if the rainfall or snowfall will get increased, the bike count will get decreased. So normalizing rented bike count column data. So we have, so here, this is a graph. So as we can see here, rented bike count has moderate right skewness, since the assumption of linear regression is that the distribution of dependent variable has to be normal. So we should perform some operation to make it normal. So we are finding outliers. So we created here a box plot to check the outliers. As you can see, there are so many outliers here. So for outlier treatment technique, so we have applied the technique on the dataset by replacing the outliers with maximum values. So here we can see by applying square root for the skewed variable in order to make it normal. After applying square root for the skewed rental bike count, here we get almost normal distribution. And here, as you can see, after applying square root to the rental bike count column, we find that there is no outlier present. This is our correlation. And now checking the correlation between variables. So we have created the ordinary least square regression. So we have imported the module and assigned the XY value here. And here we fit the OLS model. This is the correlation. And from the OLS model, we find that the temperature and dew point temperature are highly correlated. We need to drop one of them. For clarity, we use visualization, that is heat map. So here we have created a heat map. As you can see, here is the dew point temperature and temperature, which are highly correlated with each other by 0.91. And we also observe the positively correlated variables that are temperature, dew point temperature, and solar radiation. And we have also negatively correlated variables, which are humidity and rainfall. So from the above correlation heat map, we see that there is a positive correlation between columns, temperature, and dew point temperature. That is 0.91. So we drop the column. So here we drop that. As you can see, we have no dew point temperature here. Now, feature engineering and data pre-processing, we have created dummy variables. We applied one hot encoding here. Now, model training. We made the train test split for regression. As you can see here, now this is our first model, which is linear regression. So here we imported from sklearn.linear model, we imported linear regression. And here we have import the package and we set the train and test value. And as you can see, our train set R2 score is 0.79, which means our model is able to capture most of the data variance. As we have to check the R2 score, so we are going to check our test R2 score, which is 0.80. This means our linear model is performing well on data. Now for heteroscedasticity, we have plotted a residual plot, as you can see here, and this is our actual and predicted value. So orange one are actual values and blue one are predicted values. Now lasso regression, as we can see, our train sets R2 score value is 0.39 and our test set R2 score is 0.38. This is our residual plot and this is our actual and predicted values. So we have very less number of predicted values shown here. Now for ridge regression, we have R2 score for train set is 0.79 and R2 score for test set is 0.80, which also means our linear model is performing well on data. And this is our residual plot and this is the actual and predicted plot. Now for elastic net regression, our train sets R2 score is 0.64 and our test set R2 score is 0.63, which also means our linear model is performing well on this data. This is our residual plot and this is actual and predicted values. Now for decision tree, here the train sets R2 score is 0.70 and the test sets R2 score is 0.68. This means our linear model is performing well. This is our residual plot and these are the predicted and actual values of our data set. Now for random forest, our train sets R2 score is 0.98 and test set R2 score is 0.91. This is our residual plot. And here I stored all the features in our data frame called importance. So these are the features. These are the importance. This is the importance, like for temperature is 0.31, humidity is 0.16 and so on. So I plotted all these sorted values here in a graph. Like as you can see, temperature has the highest value, then humidity, and we have the least and negligible values for hour and month. And for gradient boosting, our R2 score for train set is 0.87 and R2 score for test set is 0.86. This is our residual plot. And again, I stored the values in importance and I sorted these values. And again, I put it in the graph. Again, this gives us the same value. Like temperature has the most, but here the functioning day has the second one and so on. So here is the least values. Now for hyperparameter tuning, we have imported the grid search CV from grading boosting regressor. So here you can see our train sets R2 score is 0.94, which means our model is able to capture most of the data variance. And for test set, we have 0.91 R2 score. So hyperparameter tuning certainly showed a better result. R2 was 0.91 on test, and MAE and RMSE was lower. Overall model shows good result. This is our residual plot. And again, I stored these features in importance, and I sorted it again, and I put it on the graph. And here, the temperature also has the highest number, and functioning day, then humidity, and so on. And these are the negligible values. So now this is conclusion. So during our analysis, we conducted an initial exploratory data analysis on all features on our dataset. Firstly, we analyze our dependent variable rented by count and apply transformation as necessary. So here we did this, all these, we use 7 machine learning algorithms and displaying, this is the display of our results of evaluation matrix to all models for training and test set. And here, as we can see that for gradient boosting, we have the R2 score 0.941 and we have RMSE and MAE score very low than all. So we train a model to predict the number of rented bike count in given weather conditions. First, we do the exploratory data analysis on dataset. We look for null values that is not found in the dataset and outliers and appropriately modify them. We also perform correlation analysis to extract out the important and relevant feature set and later perform feature engineering. So gradient boosting research CV model shows promising result, R2 score with 0.91. Therefore, it can be used to solve this problem. Temperature, functioning day as humidity, rainfall, and solar radiation are major driving factors for the bike rent demand. Bike demand shows peak around 8 to 9 a.m. in the morning and 6 to 7 p.m. in the evening. So people prefer to rent bike more in summer than in winter. Bike demand is more on clear days than on snowy or rainy days. Temperature range from 22 to 25 degrees Celsius has more demand for bike. So these are the insights we have found from our project. Although the current analysis may be insightful, it is important to note that the dataset is time dependent and variables such as temperature, wind speed, and solar radiation may not always remain consistent. As a result, there may be situations where the model failed to perform well. As field of machine learning is constantly evolving, it is necessary to stay up to date with the latest developments and be prepared to handle unexpected scenarios. Maintaining a strong understanding to machine learning concept will undoubtedly provide an advantage in staying ahead in future. So that's all for my project. Thank you.